Okay guys, today's warm-up says a 1.3 kilogram ball rolls across level ground at a speed of 4 meters per second. What is its kinetic energy? What is its momentum? And if it approached a ramp and then began to roll downhill, would its kinetic energy and momentum change? Explain how and or why. So that's what we're going to answer in the warm-up today. And again, after today's warm-up, we will be talking about conservation of momentum. That's our topic for the notes, which is why I'm bringing momentum back into our warm-up question. And then you will have the assignment 905.1 conservation of momentum concepts problem set that you'll be working on at the end of the period today or potentially for homework tonight, as well as part 1 of your RA if you haven't yet completed the roller coaster portion. Then you'll want to again continue working on that outside of class as well. So let's go ahead and answer today's warm-up question and then we can get into the notes. So the first question was to find the kinetic energy of this ball. And that means we need to use the kinetic energy equation, which is Ke equals 1/2 mv squared. The mass and velocity are both given to us in the question, so if we substitute those in, we get this. 1/2 times 1.3 times 4 squared, which if you put that in the calculator will give you 10.4 joules. So the answer to the first part of the warm-up, the kinetic energy of that ball, is 10.4 joules. The second part of the warm-up said, what is its momentum? And in order for us to find momentum, we need to use our momentum equation. It's been a while since you've used this equation probably. We haven't really been talking a lot about momentum. There was a couple things in the projectile motion unit where we brought that back. But the equation for momentum, in case you have forgotten, is P, that's momentum, P, equals mass times velocity. So we're simply going to plug into that equation. Our momentum equals 1.3 times 4, which is 5.2 kilogram meters per second. Okay, so those calculations should be pretty straightforward and they're not new. The last question shouldn't really be new either. If this ball then rolls down a ramp, does its kinetic energy change? Does its momentum change? What do y'all think? Does it change? Yeah, I see nods. Okay, why would its kinetic energy change?
Because the velocity goes up.
Yeah, because it gets faster. When something rolls downhill, it gets faster. If it gets faster, if its velocity increases, then that's going to change not just kinetic energy, but also momentum. Both of those equations have velocity in them. So if that ball rolls downhill, yes, it will speed up, thus increasing both its kinetic energy and its momentum. Okay, and we've talked about this before last semester, changing momentum, and we're going to talk about it again today in our notes. Okay, please make sure you have answered these questions in My Open Math, and then if you don't already have out some paper, go ahead and take it out for the notes today on conservation of momentum. But before we get to conservation of momentum, let's first remind ourselves what momentum is in general terms. Okay, so momentum, as a reminder, is the quantity of motion of an object, or sometimes we refer to it simply as mass in motion. And the equation makes sense for us to call it that. We just looked at the equation. Momentum is mass times velocity, so of course it does have to do with mass and motion. And so you can think of it as the stoppability of an object. When we talked about momentum last semester, we did a digital lab with some fan carts. And we looked at how easy or difficult it was to get those carts to stop based on how fast they were initially moving, based on their masses, based on the amount of force that was used. We looked at a bunch of different things when we did that lab. Okay, but we ultimately looked at the stoppability of the object to try to get a better idea of what momentum means. But you can also think about these questions that I have on my screen to get a better idea of what it means to have quantity of mass in motion or quantity of motion of an object. So like for example, would you rather stop a dog running 10 meters per second or a car driving 10 meters per second? If you had to step in front of one of those, which one are you going to pick? Yeah, the dog. Okay, the dog has a lot less momentum than the car, even though they're moving the same speed, because the dog has a lot less mass than a car. Okay, you don't want to get hit by a car driving 10 meters per second. I don't know that you want to get hit by a dog moving 10 meters per second either, but it's better than a car. Okay, and so you can think of that as, again, the stoppability. It'd be easier for you to get that dog to stop than that car to stop. Okay, or what about a running back when he's moving 4 meters per second versus 8 meters per second? Yeah, the slower speed. He's going to have less momentum, less quantity of motion, easier to stop him than if he's moving twice as fast. Okay, so these are the same types of concepts that we talked about last semester, but just again to remind you before we get into conservation, obviously we need to know what momentum is so that we can have a better understanding of what we're talking about when we talk about conservation of momentum. So whatever you need to jot down here to help remind you, please do so. Okay, the equation for momentum is, again, P equals m times v. That P is the variable for momentum, and it is equal to mass times velocity. Now, your momentum will change if the mass or velocity of the object changes. That's a common enough occurrence, especially when we talk about collisions. You're going to have changes in velocity whenever you have objects collide with one another. And so we're going to see a lot of change in momentum. A lot of the questions we're going to be answering are going to involve objects that are crashing into each other and therefore experiencing a change in their velocities. And thus, we're going to look at whether momentum is conserved when that happens. Do we still have the same amount? Okay, or how it's transferred or whatever is happening in those scenarios. But again, that change in momentum is common occurrence whenever you have that force acting on those objects causing an impulse. Also a term we talked about last semester. Okay, this should look familiar. I have given you the same question. I think this is the third time this year with the same picture and everything. But it says, while driving, Miss Darwin observed a bug striking the windshield of her car. The bug hits the windshield and the windshield hits the bug. Which of the two forces is greater, the force on the bug or the force on the windshield? I hear a couple different things and then I hear some mumbling back there. Abby, what'd you say? They're equal. Guys, don't fall for it. Don't tell me that the bug experiences more force. It doesn't. This is still a force pair. Okay, so again, don't tell me that the bug has more force or that the car has more force. They are equal in magnitude. Okay, equal and opposite. It is a force pair. This goes back to Newton's third law. For every action, there's an equal and opposite reaction. You have to remember this. Okay, this is a common misconception that people tend to have. And just because they have the same force doesn't mean the outcome is the same. And we're going to look at the other factors here. Okay, so this one says, same scenario, but it says to tell whether the following statements are true or false and why. We already answered A. The force of impact of the bug on the car and the car on the bug are the same size. We said that was true because it's a force pair. Okay, but what about the next one? The impulse on the bug and on the car are the same size. Okay, now if you don't remember, impulse is force times time. And we just said the forces are the same. The time has to be the same. If one of them is contacting the other one, it's the same time for both of them. Okay, and so because they have the same force and the same time, they will absolutely have the same impulse. So the impulse, again, technically is equal and opposite because that impulse has a direction to it, just like the force does. So your forces are equal and opposite. Your impulses are equal and opposite. So yes, they are the same size. They have the same magnitude. That's what that question is asking. Okay, what about this one? The changes in speed of the bug and car are the same size. Is that true? No. Drew shakes his head no. Okay, that is not a true statement. Okay, because they have different masses, they will have different accelerations, and they will therefore have different changes in velocity for that same time period that they're experiencing it. Okay, whichever one has less mass is going to accelerate more. The bug is going to accelerate more. If you're driving along down the road and you hit a bug, I don't know how fast that bug was going before, but now it's going 45 miles per hour glued to my windshield. Okay, my car, on the other hand, as I'm driving, when I hit a bug, I don't even notice a change in my speed at all. It might vary slightly. I don't know. I've never noticed it before because the mass is so small that although we have equal forces, the mass of that bug is so small, it's going to have this very large acceleration, whereas the mass of my car is so large in comparison, it's going to have this very tiny acceleration because, again, those forces are equal. So again, that was a false statement. Speed change is not the same size. The last one says the changes in momentum of the bug and the car are the same size. Again, this is what we're getting to today, guys. We're going to be talking about conservation of momentum, so we do need to talk about changes in momentum. Okay, and we already have. If you don't remember this from last semester, again, write a note down. But your change in momentum is equal to your impulse. Same thing mathematically. Impulse is change in momentum. We have impulse momentum theorem, F times T equals M times delta V, where we set them equal to each other. Okay, and so we already answered this question in part B. In part B, I said the impulses are the same, and we said it was true because they have the same force and the same time. So the changes in momenta are also the same size. They're equal and opposite to each other. They have the same magnitude. That's what we mean by same size. But what that means is whatever amount of momentum is lost by the bug is gained by the car or vice versa. Okay, so again, we're going to use that when we start talking about conservation of momentum, because in order for momentum to be conserved, the change in momentum of one object needs to be equal and opposite to the other. If one of them loses 50 kilogram meters per second of its momentum, the other one needs to gain that 50 so that the total remains the same. That's what it means for something to be conserved. Okay, so here's kind of a summary of those different relationships we just talked about. And again, you're welcome to jot any of this down that you think might be helpful to you. But again, the force on the car is equal to the force on the bug. Obviously, the time of the collision is the same. It's impossible for the car to touch the bug without the bug also touching the car. So the time of the collision and the force is the same, which means the product, force times time, that's impulse, is equal for both, equal and opposite technically. Okay, the change in momentum, same thing, equal and opposite. Okay, so the big mass, that car has a big mass, it's going to have a small change in velocity, but it will be equal in magnitude to the change in momentum of the bug. It will have a small mass and therefore a large change in velocity. And the same thing is true for acceleration. Again, you're going to have equal and opposite accelerations as well. So the car, again, big mass, therefore small acceleration. The bug, small mass, therefore large acceleration, because again, the magnitude of the forces are equal. Therefore, MA needs to equal MA in magnitude. Okay, so that's kind of summarizing everything that we just talked about. And you have to keep these concepts in the back of your mind as we are analyzing collisions today and thinking about what's happening in the collision, why the objects behave the way they do, and whether or not the momentum is conserved. This can help us to explain and see why things happen as they do. So let's talk about conservation of momentum. Okay, the law of conservation of momentum states that the total momentum of a collection of objects, that's a system, is conserved. Okay, that is, the total amount of momentum is constant or unchanging. So your total momentum will be the same before a collision as it is after a collision. It can't change. That's what it means to be conserved. Okay, so that's what our law of conservation of momentum states. The total momentum of a collection of objects, that's your system, is conserved. That is, the total amount of momentum is constant or unchanging. So it might help to look at an example. And you can see the example in the image there. I have two different billiard balls, and a cue ball is hitting a striped ball. And it says, in a collision, the momentum change of object 1 is equal to and opposite of the momentum change of object 2. That is, the momentum lost by object 1 is equal to the momentum gained by object 2, or vice versa, depending on the situation. So if we put some fake numbers to it, and we look at this scenario here, and these are just made up numbers, but we're going to go with it. It says, for example, your cue ball, which is the white one, okay, has a velocity initially after it's hit, it's moving, and it would have an initial momentum maybe of 100 kilogram meters per second. Probably not a realistic number for this image, but that's fine. We're just going to go with it. Okay, the change in momentum of that cue ball after that collision, you'll notice that it moves, but then it stops. So that means it lost all of its momentum. So its change in momentum could be negative 100, for example. The striped ball, on the other hand, is at rest when it's initially impacted. It's not moving, but it gets hit by the white ball and then it starts to move. So its initial velocity is 0, and therefore its initial momentum is 0. But its final momentum would need to be, or its change in momentum would need to be equal and opposite to the amount of momentum lost by the cue ball. So if the cue ball loses 100, the striped ball will gain 100 kilogram meters per second, and that gives you these equal and opposite changes in momentum, just like with the car hitting the bug we talked about a second ago. They will have equal and opposite changes in momentum whenever you have two objects collide. Okay, so when we talk about conservation of momentum, we can see it in a lot of different places, but this is a tool that is used to help illustrate this concept that you still have the same quantity of motion in a system. Again, if momentum is quantity of motion and it stays the same, you can actually demonstrate it with something called a Newton's cradle. If you watch this video clip, he pulls back one ball on this Newton's cradle, and when he releases it, one ball is hit and moves up the other side. But in a second, he's going to grab two of them, and you're going to notice something is like remembered about the collision, because now you have two going each side. Okay, and he does it with three as well. Okay, but you have this conservation, this same quantity of motion exists within the system. It's just being transferred from one object, or from three objects in this case, to three other objects during the collision that you see here. Okay, so this is a tool that we use to demonstrate conservation of momentum. We have one back there, but one of the fishing line came off, so it doesn't work right now. But again, you can see that you have conservation of momentum. It's demonstrated there by the number of those spheres that are kind of moving in each of those collisions. So we're going to talk about three different types of collisions. Okay, and I'm going to go through them one by one. You're welcome to jot all three of them down right now, or you can write them down as we go through them. But we are going to talk about three different types of collisions. Bounce apart collisions, like the two pool balls that hit each other. Stick together collisions, and that one there's some physics carts. He's colliding one into the other, and they literally stick together and move together. And then recoil or explosion, and that would be like this cannonball being fired from this cannon. Okay, so we're, like I said, going to go through them one by one, and I'm going to start with the bounce apart collision. Okay, so in a bounce apart collision, you're going to have, and we're going to focus only on two objects colliding. It is absolutely possible for there to be more objects than that. However, for this course, we're just going to deal with two. Okay, and so in a bounce apart collision, you have two objects collide. Maybe they were both moving, maybe only one of them was moving, doesn't matter. Okay, and then they move separately after the collision, so they bounce apart. That might mean one of them stops and the other one keeps moving, like the pool balls, or it might mean that they both are still moving afterward. Doesn't matter, as long as they're not stuck together. Okay, then you have a bounce apart collision. So the example that I have here says, let's say that a cyclist isn't paying attention when he rides his bike directly into a car waiting at a red light. And he's going to probably bounce off backwards, theoretically. So let's go through a few questions that we can think about with this scenario to apply the same stuff we were talking about a second ago. Which experiences more force, the car or the bike? They're still the same, guys. Don't fall for it. Still the same. Okay, they are equal in magnitude. It is a force pair. So same. Okay, greater acceleration though, not the same. Okay, if the forces are equal, that means that the mass times acceleration of the car equals the mass times acceleration of the bike, but the car has a very large mass. The bike, on the other hand, has a much smaller mass, and therefore the bike has a greater acceleration because it has less mass. Whichever object, and I said this before with the bug in the car, whichever object has less mass will experience greater acceleration. We're going through the same questions we did with the bug. Okay, which experiences a greater change in momentum? Y'all got to be able to answer stuff like this in your assignment today. What did we say? We should have written it down for the bug in the car. Should look familiar. They have to be equal in magnitude. Again, conservation and momentum. They have to be equal in magnitude. Or you can think of it like this. Change in momentum is force times time. It's the same force. Y'all just told me that. It's the same time. So if the force and time are both equal, then so are the magnitudes of the changes in momentum. Whatever momentum is lost by the bike will be gained by the car, or vice versa. Okay, so again, the change in momentum will be equal and opposite to one another because the total momentum in the system has to remain constant. That's what the law of conservation of momentum states. Okay, so if we have those two, they will be equal in magnitude. Greater change in velocity, same thing we just talked about with acceleration. They do have the same change in momentum. Change in momentum is mass times change in velocity, but they don't have the same mass, and therefore they don't have the same change in velocity. The object with less mass will accelerate more. So the bike will have greater change in velocity because it has less mass. So again, you need to be able to answer questions like this. Your assignment today is just concepts. There's not any math in it. Questions about this one? Okay. So to kind of summarize our bounce apart collision, and you might want to jot these points down. Again, a bounce apart collision occurs when two objects collide and move separately after the collision. One object will transfer momentum to the other, and the change in momentum will be equal and opposite. So again, if one object loses 50, the other gains 50, or whatever. Okay, so that you have the same total momentum at the end. The more massive object will have a smaller change in velocity and thus less acceleration than the smaller object. The forces in the collision will be equal and opposite. It is a force pair. The kinetic energy can be conserved for a two-object system. We haven't talked about kinetic energy with this yet, but if you do have a bounce-apart collision, there are very specific circumstances under which you can have conservation of kinetic energy. Okay, if you have other types of collisions, your kinetic energy might not be conserved. If you have any deformation, if anything gets crushed or misshapen, or if there's a lot of sound, things like that, that would indicate that you have energy dissipated, then this wouldn't happen. But in a bounce-apart collision, you theoretically don't have that, or at least not very much of that. Okay, but so you could have conservation of kinetic energy for your two-object system. It will tell you if you do, though. All right. Stick together. So I told you we're going to go through them one by one. A stick-together collision is one where you have two objects that collide and move together after the collision. Maybe they were both moving beforehand. Maybe one of them was at rest. We don't know. Okay, but if they stick together afterward, then you have a stick-together collision. For example, a semi-truck plows into a stalled car on the highway, crushing it so that they mesh and move forward together. Okay, this is why I said that the energy wouldn't be conserved, because oftentimes you have something that literally crushes and attaches itself to the other object. And when you have something that deforms like that, there is absolutely dissipation of energy. Okay, so you'll see that when we get to that summary slide at the end. But I'm going to ask you the same questions that we did with the other scenario. Which experiences more force, the car or the truck? They're still the same. Okay, they're still exactly the same in magnitude. It's still a force pair. They're equal and opposite. Acceleration, same scenario here. Whichever one has less mass will accelerate more. In this case, that's the car. The car has a lot less mass than a semi-truck, so it will have a lot greater acceleration. Okay, this is the same thing with the bug in the car as well. That scenario that I did in the notes before we started these, that's also a stick-together collision. So these answers should look really familiar. Greater change in momentum, again, equal, because it's the same force and because it's the same time. It's the same change in momentum, at least same magnitude of change in momentum. So your change in momentum will be equal in magnitude. Because your forces are equal and opposite, your momentum will be equal and opposite as well. So you'll have equal and opposite change in momentum. Greater change in velocity, again, same idea with the acceleration, whichever one has less mass. So the car would have a greater change in velocity because it has less mass and it has the same change in momentum. Are there any questions about these? It's going to be repetitive because you're going to see this, and it doesn't matter what type of collision it is, their answer is going to look the same. Okay, so let's look at a summary for our stick-together collision, and then we'll do the last type. This one says, two objects collide and move together after the collision. That's our stick-together. One object will transfer momentum to the other, and the change in momentum will be equal and opposite. We had that written down last time. The more massive object will have a smaller change in velocity and less acceleration than the smaller object. We wrote that down last time. That's still true. The forces in the collision will be equal and opposite. Still true. But the last bullet point is different. Okay, kinetic energy is not conserved for a two-object system. In a stick-together collision, because you have deformation, something got bent out of its normal shape, it's deformed and it's stuck together now, you're going to have dissipation of energy, and therefore you do not have conservation of kinetic energy. If the objects stick together, that will not happen. All right, last one is our explosion or recoil. Same thing, two different names. In this type of collision, you have two objects that begin at rest together, and some force acts to push the two apart, so they move in opposite directions. Oftentimes, we're looking at explosions. That's why it says some force, where you have a cannon firing a cannonball or a bullet being fired from a rifle. Those are very common examples, but it doesn't have to be. It can be any force that pushes two things apart from each other, and it's going to push them in opposite directions. Okay, and so here we have our cannon fires a cannonball. Which experiences more force? Katie, which one experiences more force? Cannon or the cannonball? They're both the same. Yep, still the same. Okay, so still equal in magnitude, still a force pair. Okay, greater acceleration, still the one with less mass, which means in this case the cannonball, because it has less mass than the cannon. What about change in momentum? Which one has a greater change in momentum? Still the same in magnitude. Again, that's law of conservation of momentum. You have to have the same amount before and after. So if one of them gained 50, the other lost it, so that your total remains the same. But they'll be equal in magnitude, equal and opposite. And then which experiences a greater change in velocity? Still the one with less mass. I told you it's repetitive. Okay, but don't miss these questions on your assignment then. Okay, or ones that look like this. All right, cannonball because it has less mass. Let me ask you kind of a follow-up question with this. If the magnitudes of the momentum of the cannon and cannonball are equal, what about their kinetic energy? Okay, we talked about it in the last two. Let's see, is kinetic energy conserved here? We already know that momentum is conserved. Okay, if I look at the kinetic energy equation, which variable has a greater effect on the kinetic energy of the object, the mass or the velocity? Velocity, it's squared. Okay, so theoretically, the velocity has a greater effect, okay, because it's squared in the equation. Therefore, whichever object's moving faster, in this case the cannonball, should have greater kinetic energy due to its faster speed. Okay, but we can test it. Let's put in some fake numbers. Okay, let's say the cannon has a mass of 20 kilograms, and that it moves after firing backwards at 1 meter per second. And let's say that the cannonball has a mass of 1 kilogram, and that it moves forward at 20 meters per second. And you have to set these up so that your momentum is conserved. Notice that my final momentum here is negative 20, my final momentum here is 20. My change are equal and opposite, just like we said. Okay, and so we have the same change in momentum there. So let's look at kinetic energy now, because this shows momentum being conserved. Is kinetic energy conserved? Nope. Look at those numbers. Okay, for my cannon, 1/2 times its mass of 20 times negative 1 squared is only 10. For my cannonball, 1/2 of 1 times 20 squared is 200. Okay, very different kinetic energies. So it is absolutely possible, in fact, it's usually true, that momentum is conserved, but kinetic energy is not. It is possible for one to be conserved, but not the other. In fact, the only time kinetic energy is conserved are in certain types of bounce-apart collisions. That's it. Okay, the rest of these, you're not going to have conservation of kinetic energy with a stick together or with a recoil. So just wanted to point that out. Conserving momentum does not necessarily mean conserving kinetic energy. All right, so here's our summary for our recoil. Again, both objects begin with 0 momentum because they're both at rest before the cannonball is fired. Okay, and we'll end with equal and opposite momenta after the force or explosion. So like that example, 20, negative 20, the total is still 0. Okay, the more massive object has a smaller change in velocity and thus acceleration than the smaller object. We've already talked about that. Forces are equal and opposite. We've already talked about that. Kinetic energy is not conserved in any of our recoil collisions or in any of our stick-together collisions. Okay, you will not see conservation of kinetic energy. All right, so let's do a few example problems that are kind of similar to what you're going to see in today's assignment, and then you can get on with the assignment. So if you'll take a moment, these would be good ones for you to listen up, maybe write down in your notes so that you have them to look at, because some of these are a little tricky. Concept questions aren't always easier than the math questions. Okay, so this one says, an open cart rolls along a frictionless track while it is raining. As it rolls, what happens to the speed of the cart as the rain collects in it? Assume the rain falls vertically into the box. Okay, so as this cart rolls, it's going to fill up with water. When it fills up with water, what happens to its mass? It's greater. So the question is, how does its velocity change, or does its velocity change if its mass gets greater? What do y'all think? Does it speed up, slow down, stay the same speed, or stop? Slow down. Okay, as its mass gets greater, its velocity has to get smaller in order for its momentum to remain the same. This is basically a kind of complicated version of a stick-together collision, okay, where the water and the cart are colliding, okay? And you have greater mass afterward, and that greater mass means you have to have a smaller velocity so that your momentum is conserved. Questions about that one? Okay, let's do the next one. A 7-kilogram bowling ball collides with a 1.5-kilogram bowling pin and they bounce apart. How does the rate of change in velocity of the ball compare with the rate of change in velocity of the pin? Guys, what is rate of change in velocity? That's a definition of something. What is that?
Acceleration.
That is the definition of acceleration. So I am asking you, how does the acceleration of the ball compare with the acceleration of the pin? Which one accelerates more? The pin. Whichever one has less mass, which in this case is the pin, is going to accelerate more, but that's not what the question's asking. It says, how does the ball compare? Therefore, the ball is less because the pin is more. So the ball's acceleration is less than the acceleration of the pin. This is an example of a bounce-apart collision. Again, the more massive object, that's the ball, will accelerate less than the less massive one. Thus, the ball has a smaller rate of change in velocity than the pin. This is the last example problem before you guys can work on your assignment. It says, 2 carts are held together compressing a spring between them. The spring is then allowed to expand, pushing the carts apart as shown. Which statement or statements are correct about the carts after the spring pushes them? Guys, this is an example of a recoil. There's no explosion here. It's called an explosion, but there's no explosion unless you count the spring expanding as an explosion. Okay, that's not typically what we think about, but there is a force forcing those two things apart. Okay, and they start out together. So this is a recoil. Okay, so will these carts have equal speeds? Let's start there. Are they going to be moving the same speed? I see a shaking no. Okay, yeah, you're not going to have the same speed here because they don't have the same mass. Okay, so no, A can't be true. Equal momenta. Okay, this one's kind of tricky because they would have equal and opposite momenta, but just saying equal is technically not true because negative 20 doesn't equal 20. They do have the same magnitude. If it had said equal in size or equal in magnitude, that would be true, but with the way that it's worded, we cannot select B. C says the 1 kilogram cart will move faster, and yes, it will, because it will have a greater change in velocity because it has less mass. C is a true statement, but the question could have more than one answer with the way it was worded, so let's check D. The change in momentum for each is equal and opposite, and we have said that every time. So both C and D are correct. This is a recoil collision. The more massive object will move slower than the less massive one, and momentum will be conserved. Okay, so that was just to kind of review everything that we just talked about. So, for the rest of the period today, you have the assignment 905.1, Conservation of Momentum Concepts problem set. It is due by 11:59 p.m. tonight, and you have the remainder of the class period to work on it, which is about 15 minutes. Okay, so you should be able to finish it. There's no math in there, but no math doesn't necessarily mean it's easy. Sometimes those are even trickier, so read them carefully. Work with your neighbor if you need to. If you get stuck or if you have a question, please make sure that you ask somebody, and if you don't finish it in class, it is going to be homework.